Server and data center underutilization is one of the primary sources of waste and inefficiency in computing. Data centers often use less than 40% of their available computing cycles, and yet compute resources, including servers and storage, represent more than 85% of the electronics cost in a typical data center. So think about that for a minute. If 60% of compute resources are essentially sitting idle, and compute resources represent 85% of the electronics cost, this means that more than 50% of the electronics cost in the data center is sitting idle. This represents waste and cost on a massive scale. In a web-scale data center, this can translate into hundreds of millions of dollars in wasted capex. Even a small increase in compute resource utilization translates into a huge savings in total data center capital expenditure. In our analysis, an improvement of just under 9% is equivalent to saving the entire cost of all the networking equipment. Clearly, improving compute resource operational efficiency has huge economic leverage, representing hundreds of millions of dollars in the case of a web-scale data center. In this presentation, we're going to show you a new optical data center architecture called the LightConnect Fabric vPod Data Center. This can significantly improve server and storage operational efficiency, resulting in big reductions in data center capital investment. Typical large modern data centers are organized into physical pods. These pods are usually the increment of upgrades in large data centers and typically have common failure modes like power or common cooling. Within the pod, servers and storage are organized into modular racks and rows of racks. An example pod configuration might consist of 16 rows, with each row having 8 racks of servers and storage resources as shown here. In data centers today, architects overbuild each resource pod with compute resources to handle peak demand. Workloads are assigned to pods that have the required amount of available resources to support the peak demand for that particular workload. So let's look at why servers and storage in data center are so significantly underutilized. And remember earlier that we said average rates of 40% utilization are typical. Well, first, it's because of the variability in resource demands by different services and applications. There are multiple factors in play here, but in some cases there may be a need to expand workload resources as often as several times a minute. Estimated demand, actual demand, and allocated resources are not perfectly matched. Second, capacity planning and resource allocation are based on estimation, with built-in overdimensioning and long provisioning cycles to mitigate risks. Third, virtualization limitations across networks, so for example layer 2 and layer 3 domains, can cause resource fragmentation resulting in degraded performance. The increased latency through multiple layer 2, layer 3 network hops alone degrades network application performance. And finally, compute pods typically require tightly coupled individual nodes. A single compute workload requires frequent communication between nodes, and this implies that a pod shares a dedicated network, is densely located, and probably has homogeneous nodes. So let's simplify that. These factors have two primary implications. So first of all, individual workloads should remain within a pod or cluster boundary and not be spread across multiple pods. And then secondly, as a result of this, pods typically run at low levels of resource utilization, simply to allow workloads to grow and remain within a single pod. Now, one current industry practice to improve compute utilization in data centers is to use load balancing techniques to pick up a resource-constrained workload and move it to a different pod where resources are available. But this requires policies and significant planning, and it's definitely not available on demand. It also typically generates very large east-west elephant flows between pods during the migration of the workload. And elephant flows are well known to constrain network throughput and to affect the performance of other workloads in the data center. So how can we achieve significant improvements in compute resource utilization in a practical, manageable way? Imagine if compute resources could be easily reassigned between pods at layer 1, allowing workloads to grow without the need to massively overbuild. The application workloads in most cloud data centers contain the analytics to enable preemptive reassignment of resources, so that part exists. But to make it happen, we need a way to reconfigure the optical layer connectivity in the data center to physically reconnect compute resources. This is precisely the function of CALIENT's LightConnect fabric, which allows pod resources to be reassigned at the optical layer in response to the needs of workloads. It does so with a new virtual pod or vPod architecture. The LightConnect fabric is a flat optical circuit switch network layer that sits between TORs or end-of-row switches and spine switches above the pod. It layers across multiple pods to allow sharing of resources between pods across the data center. Half of the resources in each pod in this example are static, while the other half are dynamic. The static resources are permanently assigned to each physical pod and are connected to the spine switching fabric either directly or through traditional manual patch panels. The dynamic resources can be used within the physical pod or reallocated to other pods. The dynamic reallocation is facilitated by the LightConnect fabric, a layer of pure optical layer circuit switches, effectively providing a software configurable patch panel. By reconfiguring the LightConnect fabric connections, resources within the pods can be reallocated to other pods. Thus, the dynamic resources can be considered to be a resource pool that's available to the whole data center. As an example, what we're seeing now is that pod 3 is using all its resources and is accessing additional servers and storage from a neighboring pod that has excess capacity. The LightConnect fabric simply connects 3 rows of compute resources from pod N to pod 3. Because this is all happening at layer 1, we're creating a larger compute capability within the pod and allowing workloads to expand without moving them or splitting them across domain boundaries. Conversely, a pod can give up compute resources to another pod if it has available capacity. This is the vPod concept. As compute demand grows within a pod, it can be reconfigured to borrow resources from other pods. Depending on the granularity of the LightConnect fabric, it can borrow individual racks, groups of racks, a row of racks, or multiple rows of racks by connecting them through the LightConnect fabric. The power of this approach is that it's no longer necessary to overbuild every pod with resources to handle worst-case anticipated demands. Instead, we can overbuild by an average and lower amount across the entire data center and reallocate this on demand between the pods. As a result, pods can be operated at much greater capacity and operational efficiency, and this translates directly to lower compute resource capex. vPods can be either partially or fully reconfigurable. In the partially reconfigurable case, 50% of the compute resources are directly connected to spine switches, while the other 50% are connected to the spine switches through an intermediate LightConnect fabric layer. In the fully reconfigurable case, all compute resources are connected through the LightConnect fabric. These approaches provide a very high level of flexibility in optimizing the vPod solution to the specific workloads and economics of each data center. It's also important to note that servers, storage, memory, and other compute resources can be optimized based on the vPod concept. So for example, it's possible to create a customized compute capability by pulling server resources from one pod, while storage and accelerators could be pulled from other physical pods to create a virtual pod that meets a specific workload requirement. This allows tremendous flexibility in the configuration and optimization of compute resources. A critical piece of this overall solution is the software management of the dynamic optical layer. Each resource move inside the data center requires many optical cross connections to be made inside many optical circuit switch nodes. To make this operation quick and intuitive, CALIENT has introduced the LightConnect Fabric Manager. The Fabric Manager gives the data center operator access to all of the OCS nodes that are part of the LightConnect Fabric topology. each virtual pod with associated spine switch ports, and each compute resource with associated top-of-rack or end-of-row switch ports are defined in the LightConnect Fabric Manager topology and cross-connect management modules. Resource moves are made simply by connecting the resource to the appropriate vPod with the Fabric Manager. In addition to pushing the OCS cross-connect state to each of the OCS nodes, the LightConnect Fabric Manager can trigger the push of requisite configuration changes to the top-of-rack, end-of-row, and spine switches. The Fabric Manager can be deployed as a standalone solution, allowing data center operators to make changes to the fabric as needed, or it can be integrated into existing data center resource management systems via open interfaces, including TL1, REST, SNMP, and RPC. So in this scenario, data center infrastructure administration and provisioning tools, for example, Chef, Puppet, Dockers, and others, can reserve and initiate the orchestration and provisioning of vPods through the Fabric Manager. So that's a quick introduction to the LightConnect Fabric vPod architecture, and let's just quickly summarize. So the LightConnect Fabric supports a new data center architecture, the virtual pod or vPod, and vPods allow compute resources to be shared between physical pods across the data center. Introducing vPods means that a much higher percentage of compute cycles can be utilized. This leverages a big reduction in server and storage investments, which represent 85% of the cost of data center electronics. This can only be achieved with OCS technology. It's simply not possible with Layer 2 and Layer 3 solutions because the round-trip latency of packet switching is several microseconds through every hop, and that is far too great a penalty. Thank you.